Right, in this video, I'll be talking about these four formulas: covariance, sample variance, population variance, and standard deviation. Now, when you have data like this, so over the years, you have data about, in this case, I took gold prices, some sample random numbers. If year one it was 1 rupee, and as the years progress, the gold prices increase like this, and another variable such as Reliance share price, if I take it, it has increased like this. One, it was in the year one, it was one. It was in the year 1900, it was, I just for this example purpose I took 1900 only as the price, uh, and the price has increased in this way. Now, when you want to know how these two variables, the price of gold, the price of Reliance shares, how they varied together, that is when you want to do covariance. In the sense, you want to know when this is going up, did this also go up or did this go down? So how did they jointly vary? You only want to know the direction. That is when you do covariance. The covariance doesn't tell anything else. It only tells direction. When this goes up, does this go up or down? That's the only thing it tells. So if we go to the formula for this, covariance is given by this formula. In the denominator, you can see the total number of data points minus 1. So in this case, if we have 1, 2, 3, 4, 5, 6 data points, so 6 minus 1 will be the denominator. And in the numerator, it is for the first set of data points. For each data point, subtract the average. X bar is the average of those data points. From each data point, subtract its average. Similarly, from the other data point, that is, this is for example, X is gold price, the Y is Reliance share price. Gold price minus gold price average multiplied by Reliance share price minus Reliance share price average. Product of all these, multiply these two, and then keep adding those for each of the data points. Sum of the products divided by the total number of data points minus 1. So this is x minus x bar times y minus y bar, sum of that divided by n minus 1. That gives the covariance. And it is a measure of joint variability of two random variables. If the two variables are increasing jointly or decreasing jointly, then you'll have a positive covariance. If one is increasing when the other is decreasing, then you'll have a negative covariance. The value in itself doesn't mean anything. We just need to see if it is positive or negative. And the value, just because it is big, doesn't mean it is indicating the strength of the relationship. For the strength, we need to go for correlation. Correlation will measure the strength of that relationship. That we will discuss later. And this covariance, if you see, n is a count, so this is positive minus 1, so it will be positive. But each value, when it is subtracted from the average could be bigger than the value. So the numerator can be either positive or negative. So the value of the covariance can vary from minus infinity to plus infinity. And you can use this formula when you are planning to invest, but you want to diversify your portfolio. So you're thinking, okay, how can I diversify? So in this case, you will consider different asset classes. In this case, I considered gold prices and Reliance share prices as two asset classes, and I want to check, are they diverse? Are they diverse? If I invest in both of these, did I really diversify or not? That is what I want to verify. So when I do this covariance on these two data sets, I'm getting a positive correlation, a positive covariance. So if you see here, I calculate in Excel, the covariance is 10022, which is the value doesn't mean anything, it's positive. So it means that both will jointly increase or decrease according to the sample random data I took. It means that both are increasing or decreasing. So even if I invest my money in both of these will go up or go down at the same time. So I'm not really diversified. So that is how I can use this formula to make a decision. And I need to now consider some other asset which is going down when the gold price go up, or when the gold price go down, it should go up. That is how I can diversify. If we calculate covariance of attribute X here with itself, so instead of Y, if you write X itself, the formula becomes X minus X bar times X minus X bar. So X minus X bar whole square is what it becomes, divided over n minus 1, which is nothing but this, and that is the formula for estimated population variance. So if you're measuring the variance of a variable with itself, it is population variance, an estimate of it. An estimate is when you can use the word estimate when the denominator is n minus 1. So in this case, it is estimate. And a key point to note is covariance values are sensitive to scale of data. So when you're calculating covariance, if the data is multiplied, then you'll get a different number. For example, in Python, I tried to calculate the covariance. So in this case, I imported NumPy library, put some gold prices, share prices, and some arrays, created an array, and here I tried doing the covariance, and I got this matrix, covariance matrix. So this number indicates the variance of X with itself, in the sense the variance of year-end gold prices with itself is what 1 indicates, positive, which means that both vary jointly. Obviously, it's the same variable, so they vary jointly. Similarly, this one tells year-end Reliance share prices how it varies with itself. This is one. So, and then these two, if you see, this is how year-end gold prices varies with Reliance share price. In this case, I wrote 012 and 210 opposite. So, opposite direction. So here it says uh, gold prices versus Reliance share prices. The way they vary jointly is -1. In the sense, it is only telling the direction is opposite. The magnitude doesn't mean anything. Similarly here, their opposite direction. They're going in the opposite direction is what it's saying. And in this matrix, if you see, these two numbers are actually the variances. The variance of gold price is this number, which is 1. Variance of share price, Reliance share price is 1, which is this number. And these two are the covariances because they are for the different a different combination of variables. And also you can see how I got the population variance. So let's just quickly jump to that concept first. That I'm just discussing about this other point. Let me quickly show that. So if you see here, covariance, another example that I wrote here is I just took the same array and multiplied it by 2. So instead of 0, 1, 2, 2, 1, 0, I have this data set 0, 2, 4, 4, 2, 0. So the data set is scaled up. Now when I try to calculate the covariance, you can see that instead of 1 minus 1, the covariances were earlier 1 and 1. Here we have 4 and 4 covariances. So covariance values are sensitive to the scale of data, and you should not be considering the magnitudes. You should be considering only the positive or negative parts, and then that indicates the direction is what we are trying to understand. Now that is about the covariance and how estimated population variance can also be, a formula can be uh, attained by changing this to changing y to x. We already discussed these points, and it doesn't tell how steep the line is. In the sense, covariance only tells whether both are increasing together or decreasing together. It doesn't tell are they increasing like this, uh, are they increasing uh, like this, or are they increasing like this or like this. It doesn't tell anything like that. It's only telling both are increasing in one direction or both are decreasing in one direction. It doesn't tell how steep the line is. It also doesn't tell how close the points are to the line. So if you put all the points, it doesn't tell how close the points are. It is only telling somehow they're going up or down. And for that purposes, we need Pearson correlation coefficient. Now coming to the variance, which we already discussed just now, if you plug in x and x here, you get this estimated population variance. And the actual population variance you get by this formula, x minus mu whole square by n summation of. So the total count of the data points is n, and in the numerator it is each data point minus the mean of those data points. Subtract them and take the square, sum all such squares. That is population variance. Now the variance is a measure of variability, and if we are asked what is variance, it is actually a measure of the degree of spread in the data set. So among the data points, a measure of the spread of the data is called variance, and it is more when the spread is more. The data is spread across, then the variance will be bigger. And the way to also read this formula, it says average of the squared differences between data and population mean. So average of the squares of differences between data and population mean, which is also called as mean square deviation. Mean square and deviation. So the resultant output will be squares value, so we can't really plot on a graph. And you see, if you take if the whole data set has a single number, say just one, let's say that is a data set. The variance of a same number, if you take it, it will be 0, and variance of other numbers is a squared value, the numerator, and divided by the count, which is positive because it's just a count of numbers. So when you do this calculation, variance is always either 0 or a positive value. So it is always a non-negative value, population variance. Now, because of in real world we cannot calculate population variance, we can't calculate all the data. We generally do this estimated population variance. That is, we take a sample data and then we try to calculate the variance, and then we assume that that is the estimation of the population variance. But when we're doing that, if you notice the denominator, we should use n minus 1 and not n. The reason why we use n minus 1 is that when you're calculating the variance on population, then because you're doing it with so many data points, the difference between data points and population mean will generally be larger because you're considering a lot more data points than what are in the sample. And when you take a sample, generally the differences between the data points and sample mean will be smaller because there are a few data points. You might be missing the larger differences here. But what we're doing when we're calculating sample variance is to estimate the population variance. Using this to estimate the population. But it can be a wrong estimate if we're only considering smaller differences, right? So difference will make the estimate bad. So to compensate for the smaller differences between the data points and sample mean, because we have a very small sample that we're taking related to the population data. So when calculating sample variance, we divide the sum of differences squared by n minus 1 instead of n. So we're just decreasing the denominator a little bit, and as you decrease the denominator, the total value of this formula will increase to compensate for the smaller differences, that smaller data set that we're considering, so that it will be an approximately closer to, well, it can be approximately closer to the actual population variance. That's the intention. And the way they identified this is through a lot of experiments. So through empirical evaluations is what they determined that we should be using n minus 1 for calculating the sample variance, which is also called as estimated population variance. Now, standard deviation is nothing but square root of variance. It's also called as, because you're just going to plug the square root symbol, so it is also on top of this variance. So it's also called as root mean square deviation. So RMSD, root mean square deviation, because you're putting a root on the mean square deviation, which is nothing but variance. Because variance is always 0 or positive, and we're taking square root of the variance to get standard deviation. So standard deviation is also either 0 or positive. So square root of 0 is 0, square root of any positive number will be positive number, so that is totally, we can say standard deviation is a non-negative value. And if the data is pretty close to each other, then the standard deviation of the data set will be, because the distribution of data will be like this, spread in a narrow area. So standard deviation will be a smaller number. Here you can see standard deviation is 5 for this distribution of data. And if the data is a little more spread out like this, standard deviation will be larger. And as we also discussed, standard deviation is indicated by a symbol sigma, and it is a measure of how dispersed the data is in relation to the mean. It can be either positive or 0. Now in Excel, when we calculate, we should for the population variance, which means the numerator, the denominator will be n. We can use this formula, var.p, with the data set. It is giving this value. For sample variance, we can use this formula, var.s, and the data set where the denominator will be n minus 1. For the covariance calculation, we can use this covariance.s, sample covariance, and give the first data set and second data set. Then it will try to find the covariance between these two. And for the standard deviation, we can calculate population standard deviation by stdev.p, and then the data set. And for sample standard deviation, we use stdev.s, and then the data set. You can see here that if the data set has all same numbers, standard deviation is 0. If it is having slightly varying numbers, it is in this case 5 point something, and the data set is varying significantly, standard deviation is much bigger number. And in Python, we already saw this code. and how the covariance is calculated, numpy.cov, and we need to give the array as a parameter. The array is numpy.array of the variances, and you give a list of variables here. Then that is created like this: variable 1 comma variable 2 in a list. So array needs a list as input parameter. The list can have variables. Each variable is a list in itself here. Now when you give numpy.covariance score of the array, it is calculating the covariances this way. And here if you want covariances, it is this diagonal, and if you want variances, it is this diagonal. Here. In the sense, all other elements are the variances, the diagonal is the covariance. Actually the other way around. The diagonal is the variance because it is each variable with itself. So this is actually the variance, this diagonal, and all other elements are the covariances, that is between this variable and that. This is the covariance. For the population variance in Python, I used here years, gold prices list, and tried to create an array passing the list here, list having years and gold prices as the elements where each of them are themselves a list. I displayed that, and I'm getting the arrays like this. This is the years, these are the gold prices. Now when I do numpy.var for the population variance and then the array, it is giving this. So here it is considering all the data points to calculate the variance. Now numpy.var g comma axis 0, that means it is seeing from this side and then calculating the variances. So it is calculating the variance between 1 and 1, year 1 and gold price, that is 0, and 2005 and 50. Between these two, the variance is a big number like this. Now when I do g array comma axis is 1, it is horizontal. So it is considering the data like this between the years and then calculating the variance as this number, and between the gold prices it is calculating the variance as this number, which is 2.83 times 10 to the power of 2, which is 283, and this is 5.38 times e plus 0.5, which is 10 to the power of 5, which is 1, 2, 3, 4, 5. So 538073 is the variance for the above the first row of data. Yes. Now, if you want the sample variance, the formula we need to pass a parameter to this numpy.var formula. DDOF is the parameter, and if you see the syntax for numpy.variance here, DDOF is the parameter here that we're talking about, and DDOF means delta degrees of freedom. So the divisor used in the calculation in general in the variance formula is n minus DDOF. That is over here. So variance is actually average of something. Something is absolute value between this minus mean squared, and it's typically calculated by n is length, but then if DDOF is specified, then divisor is n minus DDOF is used. And in standard statistical practice, we should use DDOF as 1 because sample standard deviation, the way to calculate is n minus 1. So DDOF, when it is 1, it becomes n minus 1. Unbiased estimator of the variance of the hypothetical infinite population is what they're saying here. So for this purpose, what we did is in the code sample variance, we gave variance and numpy dot where the array comma DDOF is 1. Then it gives is the denominator of n minus DDOF. So n minus 1 is what the denominator will become, and this is sample variance. Here I gave G axis is 0, DDOF as 1, G axis is 1 and DDOF is 1. Axis here, as we said, axis 0 means it will view from the top, axis 1 it will view from this side, and DDOF is n minus 1 in these two cases. So these two are sample variances. So these are the sample variances for the year-end price combinations. This is sample variance for the years, sample variance for the prices. And we just do a, and here if you see it's for the whole data set because we did not give an axis. And for the covariance, we just gave again covariance of the whole data set G. It gave this covariance matrix. Again, this diagonal is variances. As you can see, it is 6.45. There is the variance, sample variance for the years, which you can see here also. And 3.40 times 10 power 02 is the variance of sample variance of gold prices, which we can see here, and the actual uh, covariance is these two. So between year and gold prices, the covariance is 1 10 power 4 is what it is saying.